Hi everybody, Mrs. Pesic here. We are looking at section 5.4, rational functions. Your objectives are to graph rational functions and to transform rational functions by changing parameters. The vocabulary for this section is rational functions, discontinuous functions, continuous functions, and a hole in the graph. All right, what is a rational function? A rational function whose rule can be written, a rational function is a function whose rule can be written as a ratio of two polynomials. The parent rational function is f of x equaling 1 over x, and its graph is a hyperbola which has two separate branches. So the graph for a rational function often will look like this. This is the parent function, though, just f of x equaling 1 over x, the simplest rational function that there could be. We have graphed some like this already when we did inverse variation. If y varies inversely with x, and the product is always 20, for example, then the equation would be y equals 20 over x. And the graph would actually look, something more like this out here, a little bit further out. All right? Like logarithmic and exponential functions, rational functions may have asymptotes. The function f of x equals 1 over x has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Okay, so you do have some of this good information on your video notes, which will hopefully help you because there is a lot of information in this section. So let's take a look at this. First of all, you see that f of x equals a divided by x minus h plus some constant k is going to indicate the transformations that can occur to our parent function. So here was our parent function, and now we're making some transformation changes to it. If we add or subtract something to the x itself, like down here, when you add or subtract something to the x, that's going to be a horizontal translation. It's going to shift things to the left or right. And you know that if we add on something at the end of the function, you know that that is going to be a vertical translation. It's going to shift it up or down. And also, I think that you know that if you have some number being multiplied by your entire function, which is what's going on here, then that is going to be a vertical stretch or a vertical compression. All right? And you also know that if a is less than 0, that means a reflection across the x-axis. All right, so let's take a look at example 1. And on example 1, you're going to do this on your video notes. It says, use the graph of f of x equaling 1 over x as a guide and describe the transformation and graph each function. So if it's g of x equaling 1 over x plus 2, that indicates, because something is being added to the x, that it has been shifted to the left 2 units. So here's our original graph of y equals 1 over x. That's our parent function, but we would want to shift this 2 units to the left. So it's going to end up looking like this. That's our graph. Notice that we're going to have changes in asymptotes, and we'll talk about that in a little bit. All right, what about this one? G of x equals 1 over x minus 3. Notice now something's not being added or subtracted to the x itself, but something's being subtracted from the whole function. So what does that indicate? That would indicate a shift down 3 units. So the picture here would look like this, and the picture here, remember here's our parent function, would shift down 3 units. So it's going to look something like this. And that's the picture we have here. All right, so what I would like you to do for your notes must do number 1 is to look at these problems here and tell me what is the transformation going to be? If you have g of x equals 1 over x plus 4, write that down as notes must do 1a and describe that transformation. And then what about this one? G of x equals 1 over x plus 1. What's that transformation going to be? When you're done doing that, continue with this video. Okay, so the values of h and k affect the locations of the asymptotes, the domain, and the range of rational functions whose graphs are hyperbolas. So let's take a look at this. This is on your video notes. For a rational function of the form that we've just been discussing, a over x minus h with a plus k after it, the graph is going to be a hyperbola. There is a vertical asymptote at the line x equals h, and the domain is going to be all x's except x cannot equal h. There's going to be a horizontal asymptote at the line y equals k, and your range is going to be y such that y is not equal to k. So all y values except the k values. So let's take a look at this example. It says identify the asymptotes, the domain, and the range of the function. So please put this on your video notes. We would say, since we see a x minus 3 here, that it has been shifted right 3 units. Well, if the graph has been shifted to the right 3 units, our vertical asymptote, which was x equals 0, is now going to be at x equals 3. And then if it's been shifted down 5 units because of the minus 5, then that means that instead of having a vertical asymptote, horizontal asymptote at y equals 0, that's been shifted down 5 units. So now y would equal -5 would be your horizontal asymptote. This is your vertical asymptote here. Vertical asymptote is x equals 3, and your horizontal asymptote would be y equals -5. The domain is going to be all real numbers except for the 3. So the domain is all x's such that x is not equal to 3. That's how we would read this. And the range is going to be the set of all y's such that y is not equal to -5. All right, so there's our answers for that problem. Okay, what is a discontinuous function? A discontinuous function is a function whose graph has one or more gaps or breaks. The hyperbola graphed above and many other rational functions are discontinuous functions. All right, so it's not graphed above, but all the hyperbolas that you've seen graphed on this video have been discontinuous. A continuous function whose graph is a graph with no gaps or breaks. The functions you've studied before this, including linear, quadratic, polynomial, exponential, logarithmic functions, are all continuous functions. So if your function looks linear, looks like quadratic, looks like a nice smooth polynomial, looks like exponential growth or decay, or it looks like a logarithmic, all lovely continuous functions. Whereas if we have a graph of a rational function that's a hyperbola in 2 separate branches, well, now we've got discontinuity because we've got these gaps in between. We've got a break between the left branch and the right branch, and so on. Okay, so this next part is all about how to find the zeros and the vertical asymptotes of a rational function. So this time we're looking at a rational function a little bit differently. We're going to take a rational function of the form p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1. Then the function f has zeros at each real value of x for which p of x equals 0, and it's going to have a vertical asymptote at each real value of x for which q of x is equal to 0. All right, let's take a look at an example of this. All right, so for this example, it says, identify the zeros and the vertical asymptote. So you are putting this, write this equation on your video notes. All right, and you're going to identify the zeros and the vertical asymptotes. So to find the zeros, you basically set the numerator equal to 0. We want to know when the numerator is equal to 0. So we will say, can we factor this? Sure. This factors, you can do product sum, but it's going to be x here, 3 here, 1 here, negative and a plus. So that's the numerator factored, and it's still over x minus 2. But I want to know when is the numerator going to be equal to 0. So I'm going to set this equal to 0, and I'm going to set this equal to 0 to find the zeros. When I do that, I end up getting the zeros to be negative 1 and 3. If I set x minus 3 equal to 0, I get x equals 3. If I set x plus 1 equal to 0, I get x equals negative 1. Again, that's setting the numerators equal to 0, so my zeros are negative 1 and 3. All right, to find the vertical asymptote, we set the denominator equal to 0. So if I set the denominator equal to 0, then I get x minus 2 equals 0. I get x equals 2. And so that is the equation of my vertical asymptote. So step 2 says graph the function. All right, so to graph this function, we would plot the zeros and draw the asymptote and then make a table of values to fill in the missing points. So we would start by plotting our zeros. We had 1 at let's see, we're going by 2's here. So that's 2, 4, 6, 8. So here is the 0 that is positive 3. And here's the 0 that is negative 1. And we know we have a vertical asymptote at x equals 2. All right. And so I would like you to kind of attach a piece of graph paper or something to your video notes so you can draw this in. And then here are some of the points that we could find and plot. So negative 4 goes to negative 3.5, negative 1 goes to 0, 0 goes to 1.5, and so on. Notice they're trying to get a couple additional values very close to x equals 2. So I'll say near x equals 2. So one that's just to the left of it and one that's just to the right of it to see what's happening, right up close to this vertical asymptote. What's happening near that vertical asymptote? So I'll let you plot those points, and when you do, you will see that the graph is going to look like this, kind of curving around, getting closer and closer to that vertical asymptote. And this one also is kind of curving around, all right, like this. Okay, so I would like you to call this Notes Must Do number 2. All right, and if this is Notes Must Do number 2, I'm not going to ask you to graph this one, but I am just going to ask you to identify the zeros and the vertical asymptotes. You do not need to graph it. All right, so for this, if you're going to find the zeros, don't forget that's going to come from when you set this numerator equal to 0. And to find the vertical asymptote, that involves the denominator and setting that equal to 0. So that is Notes Must Do number 2. Okay, so now some rational functions, including those whose graphs are hyperbolas, have a horizontal asymptote. The existence and location of a horizontal asymptote depends on the degrees of the polynomials that make up the rational function. Note that the graph of a rational function can sometimes cross a horizontal asymptote. However, the graph will approach the asymptote when absolute value of x is large. All right, I know this is very confusing right now, but hopefully we can make it a little bit more clear. So this is on your video notes also. This is how to find horizontal asymptotes. So let's let f of x equal p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1. The graph of the function f has at most one horizontal asymptote. So that means there may be a horizontal asymptote or there may not, but there will be no more than one. So every rational function either has one horizontal asymptote or none. How do we tell whether there's going to be a horizontal asymptote or not? We're going to look at the degree of the numerator polynomial and compare it to the degree of the denominator polynomial. If the degree of the numerator polynomial is greater than the degree of the denominator, then there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the line y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the line that is given by this, y equals leading coefficient of the numerator over leading coefficient of the denominator. So let's take a look at some examples of this to make sure we're understanding what's going on. So example 4 says identify the zeros and the asymptotes of each function and then graph. So let's follow this rule. We have our numerator here, and we have our denominator here. We're supposed to find the zeros first. So to find the zeros, remember we set the numerator equal to 0 and solve. So to do that, we're going to factor x squared minus 3x minus 4. I know I need a 4 here, 1 here, a negative there, a plus here. So I set those equal to 0, and I end up getting zeros at 4 and negative 1. All right, I want to find the asymptotes. So there will be a vertical asymptote at x equals whenever the denominator is equal to 0. And the denominator is equal to 0 at x equals 0 because it's just x. So we have a vertical asymptote at x equals 0. What about the horizontal asymptotes? Well, that's where we need all of these rules here. So which rule are we going to follow? Is the degree of the numerator greater than, less than, or equal to the degree of the denominator? Well, the degree here is 2, and the degree here is really just 1. So that means that we really want this top case. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So here we can just say no horizontal asymptote. All right. So they've got the zeros listed. They have the only asymptote as x equals 0. That's the vertical one. And there are no horizontal asymptotes. They did do a sketch. We'll just take a look at it. And it looks something like this. All right, let's try another example. For this one, it says identify the zeros and the asymptotes of each function and then sketch the graph. And in this case, the function is x squared plus 2x minus 15 over x minus 1. And actually, for this one, the zeros we would need to factor. X here, 5 here, 3 here. That's going to be a plus, that's going to be a minus. And this is over x minus 1. To find the zeros, we're going to set x plus 5 equal to 0 and get x equals negative 5. And x minus 3 equal to 0 and get x equals 3. So my zeros are negative 5 and 3. The vertical asymptote, we're going to get that by setting our denominator equal to 0 and solving. And I get x equals 1. That's the equation of the vertical asymptote. Again, the degree of the numerator was higher than the degree of the denominator. 2 is greater than 1. So we're going to say no horizontal asymptotes. All right. Let's move on to another example. How about this one? We have f of x equaling x minus 2 over x squared plus x. And in this case, we would, again, try and find the zeros by setting the numerator equal to 0, and we get x equals 2. So there's only one zero of the function, and that's at 2. And if we want to find the vertical asymptote, we're going to set the denominator equal to 0. We would want to factor out an x, so we get x times x plus 1 equals 0. So x equals 0 or x equals -1. So those are our vertical asymptotes. We actually have two vertical asymptotes for this graph. And what about horizontal asymptotes? Well, in this case, the degree of the numerator is 1 and the degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, I'm abbreviating, then that we will have a horizontal asymptote, and the horizontal asymptote is going to be y equals 0. So if we were going to sketch a graph for this one, horizontal asymptote at y equals 0, vertical asymptote at 0, and at a -1, let me make this -1 here. So here's +1, here's +2, and so on. And so if we make a table of values, we could kind of fill in this graph. All right, and let's just take a quick look at what this is going to look like on our calculator. So it's x minus 2 over x squared plus x. I go to a graphs page. I want to get a fraction template going here. So I have my equation of x minus 2 over x squared plus x squared plus x. And there's our graph. It looks like this. Notice right here is that vertical asymptote x equals -1, and here's the vertical asymptote x equals -2, and then the graph just kind of keeps getting closer and closer like that. All right, so that's our graph for this function. All right, and one last example here. For this one, if we're trying to find, I hope you're getting all these examples down in your notes. I'm going to be checking these. For this one, the zeros, we set 3x squared plus x equal to 0. I would factor out an x. So I have x times the quantity 3x plus 1 equals 0. I set both of these equal to 0. I get x equals 0, and I get 3x plus 1 equals 0. Subtracting 1, I get 3x equals -1. So x equals -1/3. So the zeros for this function are 0 and -1/3. And if I want to find the vertical asymptote, I set my denominator equal to 0. So I say x squared minus 9 equals 0. And to solve this, I can add 9 to both sides. I get x squared equals 9. I take the square root of both sides. What do I need to remember? Plus or minus. So I get x equaling plus or minus 3. That means I actually have two vertical asymptote for this one also. X equals 3 is one of them, and x equals -3 is the other. So, and then what about horizontal asymptotes? Remember, that is when we compare the degree of the numerator to the degree of the denominator. In this case, the degree of the numerator is 2, and so is the degree of the denominator. So the degrees are equal. They're both 2, so that means we need to use that last rule that you see that says y equals leading coefficient of the numerator divided by leading coefficient of the denominator. So what's the leading coefficient of our numerator? That's 3. That's the leading coefficient right there. And what's the leading coefficient of our denominator? That's 1. So if I take 3 over 1, that's going to be the equation for my horizontal asymptote. So this is 3 over 1, which is 3. So we are going to have a horizontal asymptote at the equation y equals 3. So if we were going to graph this, 1, 2, 3, draw in your horizontal asymptote at y equals 3. We have vertical asymptotes. I think on my horizontal axis, I'm going to go by, I think I'll go by 3's here. So that's a -1, there's a -2, there's -3, there's 1, there's 2, there's 3, because I have a vertical asymptote here at x equals 3. I guess I didn't need to do that. Sorry about that. Clean that all up. So if I go 1, 2, 3, -1, -2, -3. So I'm going to have vertical asymptotes here at -3, x equals -3, here at x equals +3, and I do see that I have zeros at 0, right here, and at -1/3. They're like right next to each other, so it's kind of an interesting graph. Again, you'd want to pull up a table and plot a few points and see what happens in this. And let's take a look at the calculator to see what it's going to look like. 3x squared plus x is the numerator. (3x squared plus x), and then my denominator is x squared minus 9. All right, very nice looking graph. And if you notice here, we would have, if I can draw this in, we would have a vertical asymptote here at x equals -3, and here at x equals +3. We talked about that. And we also have a vertical asymptote at y equals 3. We talked about why that is. So we've got a horizontal asymptote at y equals 3. All right, and also it's hard to tell right now from my graph, but we have 2 zeros, one at -1/3 and one at 0. And I kind of want to prove that to you because it can't really tell from this picture. So let me just demonstrate that by going menu, window zoom. I'm going to make a window, I'm going to make a box, and I'm just going to kind of zoom in right here on this little piece of the graph, and still hard to see. Let me try this again. There we can see it. So you can see this point right here must be -1/3. This point right here is 0. You could see this going to negative, like -1/2 or something like that. So I just zoomed in on that one little piece so that you could see that. All right, so that completes the video notes for section 5.4. And I hope you took good notes. I hope you appreciated having the video notes printed for you. And I hope that you got your graphs on graph paper and your notes must do all done along with the examples. And we'll see you next time.